2021, and we will meet each other 2 hours per lectures from 3 to 5 p.m. every Tuesdays. So I hope that these lectures will be interesting for you. Okay, so my personal information is shown in this slide. You can ask me questions or any requests to this email address. And after the social distancing, we can hopefully we can meet each other. And I am available on Monday from 8 to 5 p.m., 8 a.m. and 5 p.m. And our office is now moved to building A2, and in the 4th floor, there is the divisions of organic chemistries, and I'm most time there. Okay. So the main contents of my lectures will cover the following parts. So the first part will be the infrared spectroscopy. From this time on, we will call it the IR spectroscopy. And the second part will be mass spectrometries, MS. These two parts can be found in chapter 12 in organic chemistry, written by John McMurray. If you don't keep this book, I will send you later to our Zaro group.
It is okay, since we are in the organic tree, we use the same book.
Of our lectures, infrared and mass spectrometry. Okay, the very important and very interesting part is nuclear magnetic resonance. Nuclear magnetic resonance spectroscopy, NMR. This will be in chapters 13. This is a very strong tool that we can use to elucidate the structures of. Okay, I forgot to the 请求. Going to 请求. Okay, so the last part will be about ultraviolet spectroscopy, UV-vis. And all of this can be found in this book. The contents cover 8 out of the 15 lecture days of the course. So the examples included in my lectures will be primarily those of organic compounds. And then in the second section of this course, you will spend time on learning how to use these spectroscopic methods to study the structures of inorganic compounds. And the second sections will be given by, I think, Associate Professor Chi. Yeah, so I am responsible only for the first half of this course about organic compounds. Okay, this is the book. So less than 100 years ago, structural determination was a difficult and time-consuming task. It was not uncommon for a chemist to spend years determining the structures of an unknown compounds. So before they used many years to study the structures of even very simple organic compounds. But the progress of modern spectroscopic techniques has completely transformed the field of chemistries. And now organic structures can be easily and conveniently determines after 10 or 5 minutes. Yeah. And in this chapter, we will learn how to use some simple, at the very basic levels to determine the structures of unknown organic compounds. Okay, in order to understand how spectroscopy is used for structures determination, we will first take a brief review of some of the basic features of light and matters. Light and matters. So first about light. The nature of light. So electromagnetic radiation, or simply...
Sorry, but are you speaking? We hear not.
You cannot hear me?
Vẫn nghe được ạ.
Ok, chắc là thỉnh thoảng mạng nó thỉnh thoảng bị kém em ạ. Okay, we tried. Okay, I repeat. So electromagnetic radiations, from this time on, we will simply call it light, exhibit both wave-like and particle-like properties. Electromagnetic radiations. So we have two components here, electronic and magnetics, two components, can be viewed as wave or as particles. So when light is viewed as a wave, its electromagnetic radiation, electromagnetic components are perpendicular with each others, as shown in this picture. So the red curve represent the electric wave, and the blue curve indicate the magnetic wave. And these two components are perpendicular to each others. And also they are perpendicular to the way of the direction of the light, the direction of propagation of light beams. Okay, so wavelength describe the distance between adjacent peaks of an oscillating field, while the frequency describe the number of wavelengths that pass a particular point in space per unit times. Sorry, this is so complicated, concepts in physics, so I cannot just I just read the slide, so please follow me. Okay, accordingly, a long wavelength corresponds with a small frequencies, and a short wavelength correspond with a large frequency. And we have a simple equation that show these relationships. So they have a reverse relationships. So the longer the wavelength, the smaller the frequency, and on the other way around. So this equation is quite familiar with all of you. And in this equation, C is the constant of the speed of light, just speed of light. Okay, when light is viewed as particles, its electromagnetic radiations consist of, let's say, small packs of energies called photons. So the energies of each photon is proportional to its frequencies. And this is represented by these equations. Energies equals line constant multiplied with the frequencies. And the range of all possible frequency is known as the electromagnetic spectrum. 4. Dao động điện tử. And different regions of the electromagnetic spectrum are used to study different aspects of molecular structures. So here is the simple pictures of the electromagnetic spectrum of light. So on the very on the left side, of this spectrum, you see gamma rays and X-ray. They have very high energies, extremely high energies, and can destroy many things. And on the very right of this spectrum, you have low energy light, including infrared or microwave and radios. And so from left to right, you have the increasing lambda, or the wavelength of the light. And from right to left, you have the increasing frequency. So these two factors have the reverse relationships. Okay, so this table is going to give you some of the most important application of light. So the first and very important application is of radio waves. So radio waves is the light at the very right side of the electromagnetic spectrums, on the right side. So it had long wavelength and low frequencies, remember. And this is used to study, it is used in nuclear magnetic resonance spectroscopy. And this is, I think, the most powerful methods to study the specific arrangement of all carbon and hydrogens and other atoms also in organic compound, as well as in inorganic compounds. And the second light range that is used here is infrared. This range of light is used in infrared spectroscopies to study identify the presence of functional groups in the compound. Okay. So the last kind is UV-vis spectroscopy. And UV-vis spectroscopy use visible and a part of visible and a part of ultraviolet light. UV-vis spectroscopy, vis is stand for visible. And this kind of spectroscopy is used to study the structures of conjugated pi systems. So it's very typical for organic compound. Okay, so the previous slide is about the nature of light. So light have two properties, wave and particles. And the next part is about the nature of matters. So matters, surprisingly, it's have many common properties with electromagnetic radiations. Matters also exhibits both wave-like and particle-like properties. And for me, it's till now, I'm still very confused about these quantum things. So according to the principle of quantum mechanics, the energies of the molecule is discrete. Discrete, yeah. I think I should write the word on the screen. So discrete means, I think you know the word. Discrete, it is the not continuous. So it means that the energy levels of a molecule is not continuous. It is discrete, or we use a very, it's so bad handwriting, I think. It is said quantized. So the quantized is I think it has some relation with the quantum word. I don't know which one is the original one. Dre may know, yeah. Quantum or quantile, I don't know. Okay, so to understand what this means, we will compare the rotation of a molecule with the rotation of an automobile tire. Bánh xe. So sánh sự quay của một phân tử với sự quay của một cái bánh xe bình thường, bánh xe đạp và bánh xe máy, một bánh ô tô, đúng không? So there are actually very different features of these two things. When the motor is turned on, the tire begins to rotate, and a measuring device is used to determine the rate of the rotations. And we actually can control the rate of the rotation of the tires. We can actually rotate the tire at any rate as we want. Yeah? At any rate that we want. But it is not possible with the rotation of the molecule. You cannot control it. You cannot control the rotation of a molecule. It is not understandable by the law of physics. So yeah, there's nothing to prevent us to control the rotation of the tires. But molecules have different behavior. The rotation of a molecule appears to be restricted or limited to some specific energy levels. And it means that a molecule can only rotate at a specific rate, not at any rate. And these specific rates are defined by the essential of the molecule, the nature of the molecule. And yeah, it is different from the rotation of the tire, the bicycle tires. So the rotation energies of a molecule is said to be quantized. Lượng tử hóa hoặc là năng lượng năng lượng quay của phân tử thì rời rạc chứ không liên tục, hoặc người ta gọi một từ rất là chuyên ngành, đó là lượng tử hóa không liên tục. Okay, some more things about molecules. Molecules can store energies in a number of ways. They can rotate freely in space, and their bonds can vibrate like springs. Springs là cái lò xo. Cái lò xo đàn hồi ạ. And the electrons can occupy a number of possible molecular orbitals and so on. So there are different components of the energies of molecules. So, and like the rotations, all of these form of energies is quantized. So a bond in a molecule can only vibrate at specific energy levels. So you have the pictures here to illustrate the quantized levels of of the energies. The horizontal lines in the diagram represent the allowed vibrational energies level for a particular bond. Vibrational là dao động. And you can see the short lines here. So 1, 2, 3, 4, 5, and so on. So this light represent the energy levels at which the bonds can vibrate. And the bond is restricted to these energy levels and cannot vibrate with an energy that is in between the allowed levels. So the light at the bottoms indicate low energy vibrational state, and the light at the top indicate high energy vibrational state. And you see delta E. The delta E indicates the difference in energies between the allowed energy levels. And this delta E is, as we mentioned above, is determined by the nature of the bond. Yeah. Như vậy là liên kết thì nó dao động, nhưng mà nó khác với cái lò xo đàn hồi. Lò xo đàn hồi thì mình có thể dùng năng lượng một cách tức là năng lượng mà mình dùng lực nhiều hay ít thì đều làm cho cái lò xo bị biến dạng. Tuy nhiên là cái liên kết của mình ấy, thì nó sẽ không dao động theo trong toàn bộ cái chiều năng lượng, mà nó chỉ có một số những cái mức năng lượng nhất định mà được quy định bởi đặc tính cấu tạo của liên kết đó thôi. Okay, so interactions between light and matter. Cái này là những cái mà nó rất là vật lý, thầy cũng chỉ hiểu lơ mơ thôi, nên là cũng không thể nào mà phân tích kỹ cho các bạn được. Cái này chắc lúc các bạn học môn hóa lý chẳng hạn thì chắc là cái thầy bên hóa lý sẽ giải thích cho các bạn kỹ hơn. Ở đây gần như thầy chỉ nói lại giống như trong sách thôi. Okay, in the previous section we saw that the vibrational energies level for a particular bond are separated from each other by an energy gap. And if a photon of light have exactly this amount of energies, the bond can absorb the photons to be promoted to a higher vibrational levels. So important that the energy of the photons should be exactly the same as this amount, this delta E. It cannot be larger or smaller. The energy of the photon is stored as vibrational energies unit. It is released back into the environment, usually in the form of heat. And each form of spectroscopy uses the different regions of electromagnetic spectrums and involve a different kind of excitations. So in infrared spectroscopy, we have the vibrational excitations. In UV vis, we have electronic or electrons excitations. And in NMR or nuclear magnetic resonance, we have the nuclear excitations. And this excitation corresponds to different range of the electromagnetic spectrums. They have different energy levels. Okay, so in this chapters we will just talk about the infrared radiation because they promote vibrational excitation of bonds. Okay, this is just some more thing to read at home, so I will not talk about this. Okay, we go directly to the first kind of spectroscopic method, infrared spectroscopy. Okay, first we talk about what is vibrational excitations. So there are many different kind of vibrational excitations because bonds store vibration energies in a number of ways. Bond can stretch means it can change its the bond can change the distance between the two atoms can be changed. It's like the spring when it's vibrate or when it's stretch. Cái này là dao động quan trọng nhất, là dao động hóa trị, và cái này là dao động kéo giãn hoặc là nén, làm thay đổi độ dài của liên kết. Bonds can bend in a number of ways. Yeah? It can bend like the two parts of a scissor. The two parts of the scissors can close or can open, but in one plane, in the same plane. You can imagine the two atoms and the two balls with shapes moving close to each other or far away from each other, like the two parts of the scissors. Or they can bend out of the plane. So one ball is going out, going to our eyes, and one ball is going away from our eyes. Yeah, they're different. Một cái là giống như cái kéo ấy, nó mở ra mở vào giống như cái kéo ấy, góc liên kết sẽ thay đổi giống như cái kéo, và hai cái lưỡi kéo thì nó chuyển động gần như trên một mặt phẳng, đúng không? Cái kiểu thứ hai là nó giống như là nó giống như là
ý thế là cái vòi nước ạ?
No, cái hình một là giống như cái kéo, hình thứ hai thì thầy cũng chưa nghĩ là ra là giống cái gì. Hình thứ hai thì giống như là giống như khi mà em buộc hai cái quả bóng vào hai cái dây ấy. Chúng ta xoay cái tay thì nó một quả bóng đi ra, một quả bóng đi vào.
Thì giống mình vặn vòi nước mà.
Giống vặn vòi nước ạ?
Giống cái vòi nước mà có cái vặn tròn tròn như thế, không phải là cái vặn dài.
Yeah, right. That's right. Like water twisting. Okay, twist, scissoring and twisting. Thank you. Okay, so there are many other type of bending, but we will not. I think the first kind of motion is the most important. The stretching vibration will be the most important ways to carry around here. So how to identify functional groups with infrared spectroscopies. So if you remember, functional groups is groups of atoms that are bonded with each other in a specific way. So they can bond to each other by a single bond or double bond or triple bonds. And this this functional group would have different signals in the infrared spectrum là 4. Okay. So for each kind of bond, the energy gap between the vibrational states depends on the nature of the bond. So, for examples, the vibrational state of the CH bond have a large energy gap, yeah? And the CO bond may have smaller energy gap between different vibrational states. And both CH and CO bonds will absorb infrared radiation or absorb light in the infrared regions, but the CH bond will absorb a high energy photons, higher energy photons than do the CO bonds. So in fact, each type bond will absorb a characteristic frequencies. So it allows us to differentiate which these two types of bonds. So if you have a compound that you need to study its structures, you simply radiate a small amount of this compound with all frequencies of infrared light, and then you use detectors to why CO can accept lower energy photons than the CH bond. Okay, these questions will be answered in, I think, in the coming part of the lectures, I think. Yeah, it will be answered in the coming part of the lectures. These examples just want to show you that different kind of bonds will have different energy gaps between vibrational states. It will be answered in the coming parts. Yeah, I at the moment don't have the answers. Maybe. Okay. For example, a compound containing an OH bond will absorb a frequency of infrared light characteristic of the OH bond. Một chất mà có chứa nhóm OH thì nó sẽ hấp thụ tần số hồng ngoại đặc trưng của nhóm OH. So in this way, infrared spectroscopy can be used to identify the presence of functional groups in a compound. Infrared spectrometer, máy đo phổ. Okay. I forgot to place here an image of the infrared spectrometers, but I think it's not so important. First, so in infrared spectrometers, a sample is irradiated with infrared light, and then the frequency that passed through, we say the transmitted light will be detected by the detectors, and a plot is then drawn showing which frequency has been absorbed by the samples, and then the signals will be processed by a so-called Fourier transform and give you the signals. It's not so important. So there are several techniques that are used to prepare the sample for infrared spectroscopy. The most common method involves the use of salt plates. Làm thế nào để có thể chiếu ánh sáng hồng ngoại trong cái mẫu, vì chất của mình rất là ít, đúng không? Thế nên người ta sẽ ép cái mẫu của mình ở giữa hai cái đĩa, gọi là cái đĩa với hình tròn. Và cái đĩa này thì được làm từ các cái muối kim loại thông thường. Ví dụ như là nó được làm từ muối natri clorua. Tại sao người ta dùng các cái muối này? Bởi vì đơn giản là cái muối này nó không hấp thụ ánh sáng ở vùng hồng ngoại, cho nên nó không gây ảnh hưởng đến tín hiệu của các liên kết trong chất hữu cơ mình đang đo. So đây là một cái khuôn Thế thì người ta sẽ cho muối, đầu tiên người ta cho một chút muối natri chlorua hoặc là natri hoặc là kali bromua. Thực ra bây giờ người ta hay dùng potassium bromide. Người ta cho một lớp potassium bromide vào từ trước, sau đó người ta cho cái chất của mình lên, sau đó lại cho lên trên một lớp potassium bromide nữa, sau đó người ta dùng một cái máy có áp lực để người ta nén và thành cái đĩa giống như hình tròn mà trắng ở ngay bên cạnh, nó hơi mờ đấy các bạn nhìn. Đúng rồi, cái đĩa là một muối, gọi là salt plate. Thực ra thì là bên hóa lý có máy phổ hồng ngoại, cho nên là nếu bạn nào làm nghiên cứu ở đó thì thể có thể chạy qua ngó xem các thầy cô đo mẫu thì các thầy cô chuẩn bị một cái mẫu như thế nào. Có một cái đặc điểm mà chúng ta cần lưu ý, đó là cái potassium bromide và cái sodium chloride nó rất là hygroscopic, tức là nó rất là moisture sensitive, bởi vì nó khan mà, cho nên là nó sẽ hấp thụ hơi nước rất là nhanh. Cho nên nếu mà mình xử lý mẫu không khéo ấy, thì hơi nước sẽ hấp thụ vào trong cái mẫu của trong cái đĩa muối này, và khi chúng ta chiếu ánh sáng hồng ngoại qua thì chúng ta nhớ là liên kết OH ở trong nước nó hấp thụ ánh sáng hồng ngoại rất là hiệu quả. Do đó trên cái mẫu của bạn nó sẽ luôn luôn, nếu mình làm không cẩn thận thì trên mẫu của bạn nó luôn luôn có tín hiệu của liên kết OH và nó gây nhiễu vào các cái tín hiệu chính trong chất của mình. Cho nên là đấy là cái lưu ý nhất khi chúng ta làm hồng ngoại, tránh hơi ẩm. Ở Việt Nam mình thì hơi khó tránh, nhất là những ngày nồm. Okay. So the general shape of an infrared absorbance spectrum. Thực ra những cái phần đầu vừa rồi mang tính chất giới thiệu nhiều hơn, những cái cơ sở vật lý này, rồi những cái đo đạc các thứ đấy thì thực ra là mình sẽ không thấy giới thiệu cho biết thôi. Còn những phần sau này chúng ta sẽ sử dụng để chúng ta giải cấu trúc thì nó sẽ quan trọng hơn. Okay, so the general shape of an infrared absorbance spectrum, hình dạng của một số vân phổ. So an infrared spectrometer measures the percent transmittance as a function of frequencies. This plot is called an absorption spectrum. All the signals called absorption bands point down on an infrared spectrum. Chúng ta có một cái từ mà nó gần nhau nhé. Ví dụ spectroscopy là phương pháp phổ, spectrometers là máy phổ, và spectrum là cái ảnh mà chúng ta thu được sau khi máy phổ xử lý, và cái ảnh đấy nó cho mình thông tin về cấu trúc của chất đang nghiên cứu. Thì thực ra cái spectrum là cái mà mình sẽ quan tâm nhất. Okay, the location of each signals on the spectrum can be specified by corresponding wavelength or frequencies. Long times ago, signals were reported by wavelength, measured in micrometers. But nowadays, the location of each signals is commonly reported in using wave numbers. Wave numbers. It has a symbol like this, and it has a wave. It is a wave on top. This helps to differentiate it with frequencies. It is so frequency is normally symbolized with this, and this is wave numbers. Sóng, số sóng. Có cái sóng ở trên đầu không? The wave number is simply the frequency of light divided by a constant. In this case is the speed of light. So frequency and wave number are proportional to each other. The unit of wave numbers, therefore, are the inverse centimeters. No, it is the reverse of centimeters. Chỗ này nó hơi lằng nhằng quá. Thế thì thực ra là mình có cái mối quan hệ như nào nhỉ? E dịch
Số
bằng
nghịch
HC
đảo
trên
của
lambda đúng không? Đúng rồi, thực ra nó là cái này đơn giản hơn này. Dùng phương trình này đơn giản
còn
hơn.
có cái HZ mà cái H mà Duy nhắc đến nó là tần số.
Yes, hertz. No, not hertz. Megahertz or hertz.
Okay.
Hertz. Yeah, I think it's spelled like hertz, not heart, but hertz. I think hertz. So cái ký hiệu này, cái phương trình này đơn giản hơn em ạ. Nhưng mà cái phương trình mà lúc đầu ấy nó cũng cho thấy cái sự tỷ lệ thuận của số sóng và tần số, cho nên là cũng yeah, it's hurt. Okay, so the units of wave numbers is of wave number are inverse centimeters, and the range is from 400 to 4,000 centimeters to the -1. Như vậy sau này khi mà nói đến phổ hồng ngoại thì mình sẽ toàn nói đến cm/1 thôi. Đấy là đơn vị chính dùng trong các thức gọi là phổ hồng ngoại hiện nay. Và vùng hồng ngoại, cái vùng bước sóng của ánh sáng hồng ngoại, khi mà chúng ta tính ra số sóng thì nó sẽ trong khoảng từ 4.400 đến 4.000 cm/1. Thầy cũng không nhớ cái bước sóng phổ hồng ngoại trong cái ánh sáng hồng ngoại là khoảng bao nhiêu, như thầy chỉ nhớ cái số sóng thôi là 400 đến 4.000. Okay, so please don't confuse the terms wave number and wavelength. They are actually the inverse of each other's. Wave number is proportional to frequencies, and therefore a large wave numbers represents higher energies. So signals that appears on the left side of the spectrums correspond with high energies levels. This part on the left here. So high energy. This part correspond to high energy range, because you see it has a large wave numbers, 4,000, 3,500, and this part corresponding to lower energy levels. Levels. And here you see different kind of shapes of signals in infrared, in an infrared spectrum. This is called a spectrum. This is an infrared spectrum. And as you remember from our discussions in the last semesters, every signals in an infrared spectrum has three characteristics. The first is wave numbers. The wave number indicates the position of the signals. Position. So the first is position. And the second is the intensities of the signals. The intensity indicates how strong the signal is, how large the signal is, and the last characteristic is shapes. How does the signal looks like? It can be broad or it can be shafts. So actually there are only two kind of shape: rod. Yeah, exactly. Yeah. We survived this. I think we will survive again. Okay, so signal characteristic. The first characteristic is wave numbers. So remember, the wave number tell you the positions of the signals. So first, you have to imagine that your bonds looks like springs. When you imagine your bonds is like a spring, you can understand that the wave number of absorptions is depend on two factors. And the masses of the atoms that making the bond. So this is the two ball connected by a spring. Yeah. So the bond strength and the mass of the atoms can be understood if you compare the bond with a spring, a vibrating spring connecting two balls. So using these analogies, we can construct the following equations. We call this the Hooke's law, which enable us to approximate the frequency of vibration for bond between two atoms of mass M1 and M2. So this is the frequency. No, sorry, the first one is the Fox constant. The Fox constant is another word for bond strength. Nếu mà nói về lò xo thì mình dùng gọi là độ cứng của lò xo, đúng không? Còn cho liên kết thì mình gọi là, đúng rồi, ở trong cái hóa vật lý thì gọi là K. Ở đây người ta ghi là F, chắc là viết tắt của chữ Fox. And M red indicate the reduced mass. Reduced mass is calculated by these equations. Okay, I don't know why, but if you have large, you have great. If you have great M1 and M2, you would have great reduced mass. Cái này toán học thì cũng biết tại sao, nhưng mà nếu mà M1, M2 mà lớn ấy, thì cái reduced mass cũng sẽ lớn. Còn nếu M1, M2 mà nhỏ thì cái reduced mass nó cũng sẽ nhỏ. Tại sao? Thì không biết, toán học người ta chứng minh thế. Okay, thank you. Okay, so thank you for your explanations. I think we should have a short break.
Đó là áo bắt đầu với Kusi à?
What? Cái gì cơ? Okay, thank you. Mình sẽ lao 50 phút nhé, 10 phút. Theo quy định là 10 phút.
Em thưa thầy ạ.
Yes.
Vâng,
Yes.
em xin lỗi.
Ready?